Welcome back to Shmeshapre. This is the second video in a series where I show how you can build math from the ground up, starting from set theory. Wait, the second video? Doesn't this say part 1? Yes, there's a part 0, where I explain intuitively what the sets of set theory are. Go check that one out if you missed it. I'll link the full playlist in the description. Unfortunately, we sort of hit a roadblock last time. We saw that to properly define sets, we couldn't just look at them in isolation, but had to consider the relationships between them. We saw how we could depict these relationships using a directed graph, but not just any directed graph will do. It needs to satisfy certain rules. But I have yet to tell you what these rules are. That will have to wait for the next video. Their phrasing can be quite subtle, and to do them justice, I'll first need to establish the language we'll use to precisely define these rules. This is the language of logic, and it will also be the language we use to prove mathematical statements. Let's look at the broad picture. We have certain mathematical objects we wish to describe, which are organized into networks, telling you the relationships between the objects. In our case, the objects are sets, and the networks are the directed graphs of sets we saw in the last video, telling us which sets are elements of which other sets. But the same language can be used to describe many other types of mathematical objects. To describe our objects, we form statements about how the objects of a network may be organized, called propositions. We'll see how to form such statements in a moment, but some examples are, there is a set with no elements, which we write formally like this, and there is a set which contains itself, written like this. Don't worry if you don't understand these symbols, I'll introduce them soon. On the other hand, there is a set which is blue is not a proposition, because it's not a statement we can make about sets. Sets don't have a color. Importantly, propositions don't all have to be true of our objects. Last time, we wanted to forbid sets from containing themselves, so there is a set which contains itself may not be true of sets, but it is still a proposition about sets. In fact, it doesn't really make sense to talk about whether a proposition holds except with regards to a particular network. So whenever I talk about a proposition being true or false, I'm implicitly assuming that we've fixed a network. The propositions we mostly care about are the ones that hold for every possible network of the objects we are describing. If these are our networks of objects, the statement, there is a node with no outgoing arrows, is such a proposition, since we have these nodes, for example. Such propositions obviously also include the defining rules for objects. For instance, the rules any directed graph must obey to be a network of sets are certainly propositions satisfied by all networks of sets. Well, provided the rules are propositions. We call such rules axioms. So these axioms are propositions that define our objects. But our rules for sets will include an axiom schema, our rule for generating axioms. The axioms it generates are such statements, propositions that hold for all networks of sets. But of course, usually there are more statements that hold for all networks of our objects besides just the axioms, and we'd like a way to determine what these other statements are. We do this using proofs. If we have a proof for a proposition, we know it holds for all networks of our objects, and we call it a theorem. If we don't have a proof for a proposition, that doesn't mean it's false. It may be that it holds for certain networks but not others, like the proposition, there are 6 nodes in this example. It could also be that it does hold for all networks, and there's a proof, we just haven't found it yet. So now, how do we prove statements? How do we determine which propositions are theorems? We do this using derivation rules. These allow you to derive new theorems from some number of old ones. These include rules that are specific to the objects we are studying, like our axioms and axiom schemas, as well as rules that hold regardless of what our objects are, the rules of logic. The simplest type of derivation rule lets you derive a theorem without requiring any prior theorems. For example, given a set axiom, we might have a rule that lets us derive that axiom. But we can also have logical axioms, which work similarly, but are not specific to our objects. In order to prove a statement, we start with the statements we can prove from nothing, our axioms. Then we apply derivation rules to prove new statements from our axioms. Then we apply more derivation rules to prove new statements from those statements, and so on. Eventually we prove the statement we care about, and then we know that that statement does indeed follow using our derivation rules. We say that that statement holds for every network of these objects allowed by our axioms, and we call it a theorem. Got all that? Okay, I have a confession to make. Ultimately, we're never going to deal with these objects, or the networks thereof, directly, and whether or not they're real in some sense is up for debate. We're really only going to be working with these statements, which themselves are really just sequences of symbols on a page or screen, with a list of rules telling us how we can manipulate them to get other sequences of symbols. But it may be helpful to think of them as statements describing something real. So whenever I talk about these networks of objects, I'm being very loose and just trying to build an intuition. If you find it helpful, great. If not, ignore it. Okay, now what are all the possible propositions we can have? The way we construct propositions is rather similar to how we construct theorems. We start with certain basic propositions that we can form from nothing, and then we have rules that let us construct new propositions from old ones. Well, we're actually going to need a slightly more general concept: predicates. If a proposition is a statement about the objects of a network, then a predicate is a property that certain such objects can have. But let's put predicates aside for now and look at what propositions we can build without them, starting with our two most basic propositions, true and false. Don't ask me why false is written with an upside down T instead of an F. For some reason, that's a standard notation. Anyway, true is a proposition which is trivial to prove. We can take it as a logical axiom, giving us our first derivation rule. We can always derive the statement true. On the other hand, false should ideally be impossible to prove. I say ideally because it's hard to ensure that something can't be proven, except by only having very few or very weak derivation rules, and then you can hardly prove anything interesting at all. Adding rules only lets you prove more things, not less, so there's no way to add a rule that false can't be proven. If false can be proven, it means there are no networks of objects that satisfy all the axioms for these objects, and we say the axioms are inconsistent. So far, I haven't introduced any rules for false, but we'll see one later. Now, let's look at ways to construct new propositions from old ones. Our first is conjunction. We can combine two statements into one using and. Given two propositions P and Q, we can form a new proposition P and Q, written with this wedge symbol, which is a statement that P and Q both hold. If you feel uneasy that I've used and in defining the statement P and Q, keep in mind that and is just the name we've decided to ascribe to this particular way to combine statements, and the reason we picked that name is because the way it works is similar to the English word and. The same will be true for the other ways of forming statements we'll see shortly. We can split the rules for and into introduction rules, telling you how you can prove P and Q, and elimination rules, telling you what you can prove if you know P and Q. In this case, we have one introduction rule. You prove P and Q by proving P and proving Q. And we have two elimination rules. First, from P and Q, we can derive P, and second, from P and Q, we can derive Q. Many but not all of the other rules we'll see will be split into introduction and elimination rules like this, with the introduction rules telling you how to prove propositions of a particular form, and the elimination rules telling you what you can prove if you know a proposition of that form holds. For instance, our rule for true was an introduction rule. It turns out true has no elimination rules. This and might not seem very useful yet, so let's look at a perhaps more useful way of combining propositions: implication. Given propositions P and Q, we can form the proposition P implies Q, or if P, then Q, written with this arrow. The elimination rule for P implies Q is as follows. From P implies Q and P, we can derive Q. So P implies Q tells us that should we ever manage to prove P, we can also then prove Q. Why is this useful? Well, let's say you want to prove some proposition Q. This lets you split up the work into two, hopefully easier, steps, which you can do in any order, proving the statement P implies Q and proving the statement P. This works for any statement P of your choice, but of course not all of them will make your work easier. We also have an introduction rule for P implies Q, but it's more involved and doesn't fit the same from blah, derive blah format of the rules we've seen so far. You prove P implies Q by assuming that P holds, as if by axiom, and then proving Q using it. Once you're done, you're no longer allowed to use the assumption that P holds or anything you derived from it, since you don't actually know that P holds, but can now use P implies Q in the rest of your proof. I think it's clear what's going on if we draw some boxes. To prove P implies Q, Draw a box and write P at the top with a line underneath. This is your hypothesis. Inside the box, continue your proof as usual. Here you may use anything from outside or inside the box, including the hypothesis P. However, you cannot use anything from inside the box to prove anything outside the box, unless you append P implies in front. So if you prove Q inside the box, you can take it outside the box, but only as P implies Q. You can nest these boxes within each other, and the same rules apply. Next, disjunction. Given propositions P and Q, we can also form the proposition P or Q, which tells us that P is true, or Q is true, or both. That is, P or Q holds for a particular network when P or Q or both hold for that network. It's not necessarily the case that if P or Q holds for all networks, then P holds for all networks, or Q holds for all networks. There could be some variety. We have two introduction rules. From P, you can derive P or Q, and from Q, you can derive P or Q. We also have one elimination rule, which tells you can split a proof into cases. Let's say you know P or Q and want to prove another proposition, R. You can do it by proving that R holds assuming P and that R holds assuming Q. That is, you treat the case where P holds and the case where Q holds separately, and get a proof for R without needing to prove either, only the statement P or Q. In short, from P or Q, P implies R, and Q implies R, we can derive R. Note that if you combine ands and ors and implies together, you may need to add parentheses to indicate the order of operations, because, say, P and Q or R is different from P and Q or R. The first tells you that P is true and either Q or R is true, and the second tells you that either P and Q are both true or R is true. Next, we have negation. So far, I've talked about how we can prove statements, but not how you can disprove them. That is, show they hold for no networks of R objects. The way we disprove the statement P is by proving the statement P implies false. That is, P leads to a contradiction. We can abbreviate this like so, read as not P. The statement that P is false. We need one additional rule here. If P is not false, then it's true. That is, from not P, we can derive P, which is of course short for this. This is the rule for false I promised. This rule tells us we are working in classical logic. If we remove this rule, we get what is called minimal logic. And if we replace it with a weaker rule that anything follows from a contradiction, that is, from false, we can derive any proposition P, we get constructive logic. I'm not going to explain in this video why you might want to work in minimal or constructive logic. I'm just mentioning them here to let you know they exist. We're going to be working solely in classical logic in this series, so that's all we need to know. There's one more abbreviation we commonly make, equivalence. For propositions P and Q, we write this, read as P if and only if Q, to mean P implies Q and Q implies P. That is, we can derive each of P and Q from the other. With the rules we've established so far, we can form propositions like these. But these don't really say anything about sets. To construct more interesting statements, we'll need to look at predicates. A predicate is a property that some number of objects can have, without specifying the objects in question. Again, in our case, these objects are sets. A predicate is like a proposition, but its expression might contain some number of variables, standing in for the sets in question. We can use whatever symbols we want for these variables, as long as they can't be confused with anything else, but we're most often going to use lowercase letters like ABC or XYZ, possibly with subscripts or tick marks. A predicate in a single variable is a property that one set could have, say the property of being empty. As written here, this is a predicate in the variable x. Y here is a bound variable, so we don't count it. More on that later. A predicate in two variables is a property that a pair of sets could have, say one being an element of the other. Here, this is a predicate in the variables x and y. A predicate in three variables is a property that a trio of sets could have, and so on. you can form a proposition from a predicate by specifying the sets in question. This is the statement that the sets you have specified have the given property. A predicate in 0 variables is just a proposition. There aren't any sets you need to specify. A predicate in some variables can always be thought of as a predicate in more variables. So for example, true and false can be thought of as predicates in any number of variables. The variables don't need to appear in the expression, but we must count every variable that does appear, excluding bound variables. All the ways of forming propositions that we've seen so far carry over to predicates. If P and Q are predicates in the same variables, then we can form predicates P and Q, P implies Q, and P or Q in those same variables. If P and Q are predicates in different variables, we can always consider them as predicates in more variables, such that their variables do match. For example, if P is a predicate in x and y, and Q is a predicate in x and z, we can consider them as predicates in the variables x, y, and z. So, say, P implies Q is also a predicate in x, y, and z. We can also define not P and P if and only if Q in a similar way as for propositions. Okay, I guess I should introduce the concept of terms, too. A term is an expression involving some number of variables that represents one of our objects, say a set. An easy example of a term is a variable by itself. So if we have a variable v, then v itself is a term in the variable v. As with predicates, it can also be thought of as a term in more variables. So for example, x is a term in the variables x and y. In fact, in set theory, the only terms we have are variables. So you can just replace everywhere I say term with variable, and it'll be just about right. So why am I introducing terms if they're entirely superfluous in set theory? Well, if we want to extend this to be able to talk about mathematical objects besides sets, then we might have more terms specific to those objects. If we wanted to describe the natural numbers, say, instead of sets, in addition to variable terms, we might have constant terms like 0 and 1, and ways of combining terms to make more terms, like addition and multiplication. So this, which is 2x plus 1, would be a term in the single variable x. But again, with sets, the only terms we have are variables. Okay, let's see what new types of predicates we can form. Because many of these have more complicated rules than what we've seen so far, I'm going to introduce all the types of predicates we need first, then introduce the rules for them after. We have a new basic predicate, equality. If s and t are terms in the same variables, then s equals t is a predicate in those same variables. This tells us that s and t are in fact the same object. If, as for sets, our only terms are variables, the predicates we get are all of the form v equals w, where v and w are variables. When dealing with sets, we have another basic predicate, membership. Given terms s and t in the same variables, we have a predicate s is an element of t, or s is in t, in those same variables. That is, for variables v and w, we have predicates of the form v is an element of w. We also abbreviate not s equals t, like so, read as s is not equal to t, and not s is an element of t, like so, read as s is not an element of t. If we wanted to describe something other than sets, then instead of this membership relation here, we might have some other basic predicates. Next, we have universal quantification. Given a predicate p and a variable v, we can construct a predicate for all v, p, in the variables of p excluding v. This tells us that all objects of the network have the property p. For example, we know x equals y is a predicate in x and y, so for all x, x equals y is a predicate in y. Even though x appears in this expression, we say that it is a bound variable, and don't count it towards the number of variables in this predicate. We only count free variables, which are the variables that are not bound, in this case just y. Or rather, we are entitled to only count free variables, although as we saw earlier, we may always consider it as a predicate in more variables. So we can also consider this as a predicate in x and y. It's just that x happens not to appear in this expression as a free variable. Next, existential quantification. Given a predicate p and a variable v, we can similarly form a predicate there exists v such that p, in the variables of p excluding v. This tells us that the network contains at least one object with a property p. Again, v is a bound variable here. Okay, let's recap. We start with our basic predicates, true, false, v equals w, and v is an element of w, where v and w are variables of our choosing. We can combine two predicates into one using and, or, and implies. We can also turn a predicate into another with one less variable using for all and exists. Once we run out of variables, we are left with the predicate in zero variables, a proposition, and these propositions are the statements we care to prove. Before I give the rules for these new predicates, we need to talk about how to replace a variable in a predicate with a particular term. I mentioned you can get a proposition from a predicate by specifying the sets in question, but how do you do that exactly? Let's say t is a term, v is a variable, and p is a predicate. Then we write this here to mean the result of replacing every free instance of the variable v in the predicate p with the term t. On the right of the slash, we have the variable we are replacing. On the left, we have the term we are replacing it with. Got that? So if we have this expression here, we replace every occurrence of x with y to get this. We only replace the free instances of our variable, not the bound ones. In a predicate like this, the first occurrence of x is free, but the latter two are bound. They are completely different x's. We've just decided to use the same variable name for two different things. So if we replace x in this expression with z, like so, we get this, where the first x is replaced, but the second and third are unchanged. The best way to avoid this confusion, though, is of course to avoid reusing variable names like this. Remember our rule for implies that involve drawing boxes? We're going to introduce a very similar rule shortly, but with variables instead of propositions as assumptions. It'll be easier to state our rules if we change our terminology slightly. From now on, for the purposes of any rule we apply inside such boxes, when counting the variables in a predicate, we're going to ignore the variables that are introduced in these boxes, and only count the free variables that are not introduced. So whereas this is usually a predicate in the two variables x and y, if we're working inside a box where we've introduced the variable x, we'll call it a predicate in the single variable y. And if we're working inside another nested box where we've introduced the variable y, we'll call it a predicate in zero variables, or a proposition. Also, from now on, whenever I refer to a term, I mean a term where all variables are introduced in the boxes our rule applies in. So in set theory, a term is an introduced variable. Here, x and y are not terms, since neither of them have been introduced. Here, x is a term, but y is not, since we've introduced x but not y. And here, x and y are both terms. This of course means that what counts as a proposition, a predicate in a particular number of variables, or a term for the purposes of our rules, depends on the context in which those rules apply. Okay, now let's see the rules for the new predicates we introduced. Let's start with for all, whose introduction rule is quite similar to the one for implies. Draw a box and write v at the top with a line underneath, where v is some variable not yet introduced. Inside the box, you can use anything outside or inside the box. If you have a statement inside the box and want to use it outside, you must append for all v to the front. This p is a predicate in v, which we consider as a proposition inside the box. Essentially, to show something holds for every set, we suppose we are given an arbitrary set that we know nothing about, and show that it holds for that set. Now the elimination rule. If p is a predicate in the variable v and t is some term, then from for all v p, we can derive that p holds with v replaced by t. If every set has the property p and t is some set, then t has the property p. Next, exists. To show something exists, you give an example. So the introduction rule for exists is that if t is a term, v is a variable, and p is a predicate in v, then if p holds with v replaced by t, we can derive that there exists v such that p. What about the elimination rule for exists? Well, it's similar to our proof by cases for or. If you want to prove some statement q, you suppose you have a set with a property p and show q holds. Then we know q holds regardless of the particular set you fixed. That is, suppose v is a variable not yet introduced, p is a predicate in v, and q is a proposition. If we know there exists a v such that p, and for all v, p implies q, we can derive q. Now the rules for equality. The introduction rule for equality is that every object is equal to itself. For every term t, we have that t equals t. The elimination rule is that if two things are equal and one has some property, then the other does too. That is, suppose we have terms s and t, and a predicate p in the variable v. If s equals t and p holds with v replaced by s, then p holds with v replaced by t. The rules for membership are the axioms of set theory, which I'm saving for the next video. So yeah, those are the rules. There are a few more things I'd like to add, but that's enough for this video. See you next time.